For our final chapters of this semester, we'll discuss some analytical measurements and analytical techniques that are appropriate to analyzing a particular analyte. To begin, we'll talk about assessing the quality of an analytical technique or measurement. The first we'll discuss is the limit of detection, or LOD. This is the minimum detectable analyte amount. Any less than this limit of detection, and we cannot distinguish differences in analyte concentration. Next, sensitivity. The sensitivity of a technique is how good that method is at distinguishing differences in signal from our analyte of interest versus some sort of interference, which could be caused by variations in that analyte's concentration, or could be caused by noise from our instrument. And we'll talk a little bit more about signal to noise ratios as we move forward. Thirdly, the dynamic range for our technique is the span from the limit of detection to the point beyond which we can no longer receive a linear response from our technique. If we were tracking a signal from an analyte of interest as a function of that analyte's concentration, our dynamic range would span from a point here that starts a linear increase along this signal to concentration plot, beginning at the limit of detection, the smallest detectable analyte concentration, and ending where this line is no longer in the linear range. This whole span is the dynamic range. Lastly, we discuss selectivity. This is the ability of a technique to distinguish between two different analytes, or to detect an analyte alone selectively in the presence of other analytes that we might not be interested in. When we discuss specific techniques of analysis, the first we'll encounter is spectroscopy. Spectroscopy is the use of light, either light absorbed or light produced by an analyte. Light being absorbed by an analyte takes advantage of absorption spectroscopy, while light being produced by an analyte takes advantage of emission spectroscopy. We'll talk about emission spectroscopy first, and we'll discuss how an emission spectrometer works, what it's made of. In an emission spectroscopy experiment, you, or an instrument that you use, needs to supply energy to an analyte of interest to force that analyte's electrons into excited states. You can do this through use of heat, like from a flame, or light itself. Ultimately, emission occurs because excited state electrons relax back down to ground states. When they do so, they emit photons, and we can measure those photons' wavelengths. An example of an emission process might look like a sodium atom having an electron move from an excited 3p orbital into a 3s orbital. The wavelength of a photon emitted from this process is 589 nanometers, a characteristic line for sodium. In this depiction, an asterisk next to sodium indicates that this is a sodium whose electron configuration is not in its ground state and is rather an excited state electron configuration. Emission spectroscopy takes advantage of this excited state electron configuration. In order to build an instrument that's capable of measuring the wavelengths of photons produced from excited states as they relax electrons and emit photons, we need several key pieces of equipment. A schematic for such a device looks like this. Our emission spectrometer is comprised of some excitation source, maybe a flame, to which we expose a sample that contains our analyte. This excitation source excites our sample and places our sample or its analyte contents in their excited electronic state. This sample, once removed from the excitation source, will have electrons that relax back down to a lower energy state. And as they do, they emit a wavelength of light or multiple wavelengths of light. And we send that light to a monochromator or diffraction grating that separates multiple wavelengths of light into individual components. Those individual components can be analyzed by a detector to determine what wavelengths they are or what the intensity of a particular wavelength is. So here are those defined. A monochromator is a diffraction grating, like a prism, that separates incident or incoming light into component wavelengths, while a detector identifies wavelengths through some independent instrumentation of its own. And we'll talk about different designs of detectors as we move forward. In contrast to emission spectroscopy, an absorption spectroscopy experiment, like UV-Vis, relies on an atom or molecule absorbing a photon of light, causing electrons in analytes to jump into excited states. Our approach in this technique is to measure any light wavelengths that are not absorbed by our sample, to deduce which wavelengths were absorbed. A simple schematic for an absorption spectrometer looks like this. We have some radiation source that might be a simple light bulb or tungsten filament. That radiation source produces broad spectrum light. And if you aren't already familiar with this, H nu is light. It's the energy of a photon of light. It sends in a photon or a broad spectrum of photons of light incident upon a sample that contains an analyte we're interested in. That sample absorbs some of the photons of light of particular wavelengths, and only those photons that are not absorbed make it out and are able to travel to a monochromator and be dispersed into wavelengths detectable by a detector. It's possible to modify this schematic slightly to show our radiation source simultaneously influencing both a sample and a blank, or a material that contains just the matrix that our analyte is in. A schematic for an instrument that analyzes a sample and a referencer, blank cell simultaneously, is shown here. All of the same information gets passed to a detector so that we can distinguish or differentiate between any light that our sample absorbs due to both analyte and matrix versus light that just our matrix is absorbing. Absorption experiments are useful for chemists because we can often quantify through a relationship known as the Beer-Lambert law how concentrated an analyte is in a particular sample based upon the degree to which it absorbs light. Beer's law, or the Beer-Lambert law, tells us that the radiant power P for light absorbed by an analyte is directly related to the concentration of an analyte. We're going to use that here to develop Beer's law. We're going to make two assumptions here. For one, we'll assume that any incident light that hits our sample or analyte in the first place is monochromatic, so that our radiation source has been sent through a monochromator of its own to deliver just a single wavelength at a time to our analyte. And anything in our analyte that absorbs light, atoms, molecules, don't interact with each other and are independent in this process. A quick sketch of what this might look like is here. Here, we're going to have some source that delivers an initial power, P0, of light of a single wavelength incident upon our sample. Our sample has a length B that light must travel through before it emerges on the other side. And as that light travels through the sample, some of the photons are absorbed, so that at the end, emerging light with a nominally different power, just P now, is left. As this incident light impinges on our sample, it starts to have some of the photons associated with it absorbed. And as some photons are absorbed, the power of this incident light drops off incrementally. We can think about taking a really tiny little sliver of our sample, maybe just this tiny little bit, and thinking about how much power passes through just that tiny little sliver. So if I redraw that, then that's some incident light passing through now, just a teensy tiny little piece, an infinitesimally small piece of our sample. It's so small that it's now not really the length of our sample anymore, but rather an increment in length, dB, or a differential in the length. Any light that travels through this incrementally small path length of our sample must be produced from the other side in a concomitantly decreased power. So what comes out of this is our initial power less some small change dependent upon the length of that increment, dP. Thus, a decrease in the power of our incident light is proportional to this length, this incremental cross-sectional thickness, the incident power itself, how much we started with, and how much is lost to our sample as that light travels through here in the first place, which in turn is related to how concentrated our sample is. We'll call concentration C here for the purposes of the math that we're about to do. Because this loss or change in power, this drop off in our incident light's power is proportional to our original incident power, this increment in path length and concentration, we can set up an equation that relates all of these together. The equation looks like this. Our change in power, dP, is equal to a negative value, negative because we're decreasing the original power. Negative value of some constant K. This is a constant of proportionality, multiplied by the power that our light is at now, the concentration of our sample, and the increment in the path length that we've covered. To solve this equation, and to start to explicitly include P0, we need to arrange like terms on the same sides of this equation and integrate. So what I will do is bring terms of P to the left-hand side and keep everything else on the right. I'll bring a negative P over to the left, and on the right we'll have some constant that relates these quantities together times analyte concentration times an increment in path length that light travels through our sample. We're going to integrate these two sides, the left-hand side from our initial power that was incident on our sample to the power that emerges as this light has passed through our sample. On the right-hand side, we're going to integrate from the bounds of 0 before our light entered our sample to B when light has passed all the way through the entire length of our sample. The left-hand side integrates as the negative natural log of P, evaluated over the bounds from P0 to P. The right-hand side has two constants, K and C, that can come out. We integrate dB from 0 to B. Another way to express this is by plugging in our bounds of integration. We have the negative natural log of P divided by P0. Because the natural log of x minus the natural log of y can be rewritten as the natural log of x divided by y, so that the natural log of p minus the natural log of p0 can be rewritten as the natural log of p divided by p0. On the right-hand side of this equation, we've simply got k times c times b. This equation, the Beer-Lambert law, relates some nebulous term, the negative natural log of emerging power relative to incident power of light, to three constants. It's important, though, that we point out that this ratio, P divided by P0, is called transmittance. And if we multiplied this by 100, P divided by P0 times 100 is the percent transmittance. If you've done FTIR experiments, you've likely seen graphs or data presented in percent transmittance. It can be useful then if we can express this percent transmittance through a quantity that's a little bit more direct. What we're going to do is change the base of this natural logarithm to base 10, a log base 10 instead of base e, and rearrange the equation that we've got there. The actual math of how we do that isn't quite as important as the quantity we end up with. As we change the base of this formula, we end up switching our fraction to get rid of our negative sign. And instead of k on the right-hand side, we'll have a quantity epsilon times b times c. This is the more important version of this integrated equation. Here, this new quantity epsilon is called the molar absorptivity of a material. This is a substance-specific quantity that is tabulated for given substances. It has units of liters per mole per centimeter of path length. B is the path length that light travels through a sample. Often, this path length is set by the device that we use and is typically 1 centimeter. C is the molar concentration of our analyte. And lastly, as we manipulate the percent transmittance, or simply transmittance of the light through our sample, and rearrange it to the log base 10 of P0 over P, we refer to this quantity as a phenomenon called absorbance. Just capital A. Thus, the final form of the Beer-Lambert law looks like this. Instead of the log base 10 of P0 over P, we can simply write A. The absorbance is equal to epsilon times B times C. Because epsilon and path length are nominally constant for a particular analyte, we expect that in a dynamic range, where we can measure absorbance linearly with concentration, a Beer's law plot will help us identify what the concentration of an unknown quantity of analyte is, given its absorbance. You generated such a plot in general chemistry and showed that absorbance versus concentration can be linear over a wide range for a particular analyte. At this point, I'm sure you're wondering how you choose between absorption and emission. They both seem like such great experiments. Why would you ever choose one over the other? There is a fundamental difference between these two spectroscopic approaches, And we can illustrate that difference through some analogies. First, let's think about absorption. Imagine that there is no coronavirus and 50,000 people are together in a stadium at night, all with just flashlights on and no stadium lights shining. We might expect then that, for analogy purposes, the incident power from all of those flashlights is 50,000 arbitrary units. Suddenly and simultaneously, 500 people in the audience turn their flashlight off. Compared to the original power, the new power, just P, is effectively 50,000 minus 500, or 49,500. The transmittance is the ratio of the new power to the original power, 49,500 to 50,000. That's 0.99 or 99% of the light that was coming still got through. Absorbance, A, is the negative log of transmittance, or the negative log of 0.99. This is a really small quantity. It's almost 0.004. In other words, this is barely observable. An absorbance value should be somewhere close to at least 1/10 to be appreciable. And we can probably imagine that having 500 out of 50,000 people turn a flashlight off while everybody else keeps theirs on is going to be barely detectable to the human eye, too. So let's develop a similar analogy to do the same sort of test through emission. In this analogy, 50,000 people are sitting in a dark stadium, again, away from coronavirus. Suddenly and simultaneously, 500 people turn on a flashlight. This sounds already intuitively like it's a whole lot more detectable than our previous analogy. Here, our excited population, or the number of flashlights that are on, is 500. Our ground population, or lights that aren't shining, is what's left over, 49,500. The ratio of the number of excited states to the number of ground states is 500 over 49,500. That's approximately 1%. And what's more is that this 1% is not dark against a light background, but rather light against a dark one. The contrast makes this much more detectable. In general, what we can say then about absorption versus emission experiments is that when we expect lower signal intensity from our analyte of interest, like flashlights, then an emission spectroscopy experiment is a better approach than an absorption spectroscopy experiment. If there's a large difference in intensity between two sources, like if we had half of all people sitting in a fully lit stadium turn off their flashlights, then absorption is fine. We might choose to conduct an absorption experiment because it's generally cheaper and easier and more readily available to do so. Also, it's less destructive to a sample. What we can explicitly say then is that emission experiments generally have a better limit of detection compared to absorption experiments. The sources of light or energy that are used in spectroscopy experiments differs typically depending on whether we choose to employ an emission or an absorption test. In an emission spectroscopy experiment, we need to excite electrons, so we need a whole lot of energy to do that. Often we'll use something like an acetylene and air flame. Acetylene is C2H2 mixed with air. A flame of acetylene can burn to about 2500 Kelvin. Alternatively, we can employ a plasma that generates higher temperatures and can excite virtually any substance. An argon plasma is unlikely to react with analytes of interest, and this excites virtually everything. The drawback of an argon plasma, though, is that it's expensive. So while a plasma is good at exciting things that aren't necessarily affected by a flame, a plasma is also expensive to set up and to maintain. Absorption experiments don't rely on having to impart energy, but rather to shine light on a sample of interest. For atomic analytes, single atoms, we might use a hollow cathode tube. This is a selective tube that generates a very narrow wavelength range and can be used to parse for information regarding a specific atomic analyte that we might be interested in. If, however, we're performing absorption experiments on molecules, we might want to use broad spectrum light, like a black body, to generate a full spectrum of white light. This black body or broad spectrum light source that could be a simple white light bulb, or maybe includes a UV light generating source, is used for molecular spectroscopy because molecules are more complex and will absorb differently depending on their molecular structure. If we employ UV or ultraviolet light in an absorption experiment, then we need to make sure that any light that's produced is capable physically of traveling to and being potentially absorbed by our sample. We need specialized glassware that's transparent to ultraviolet light, like quartz silica, which can be rather expensive. And so often, if we can get away with just using visible light, which can pass through simple glass, then we'll do so for absorption experiments. Lastly, let's discuss the detectors that might be used in an emission or absorption experiment. The choice of detector is independent of the experiment type that we choose, because in both experiments, all we're interested in detecting are wavelengths or intensities of light. Common detectors operate on the basis of the photoelectric effect, which you probably remember from general chemistry, says that when light hits material, it can cause electrons to become mobile. When light hits a detector and causes some electrical response, we can register that response as, say, a voltage that can be used to track signal intensity. Two common types of detectors used in spectroscopy include a vacuum phototube, which contains all the electronics to undergo this photoelectric effect in vacuo, or a photomultiplier tube, which uses a cascade of electrical responses to amplify the gain associated with an electrical response. So, to round off this section on spectroscopy, let's discuss what happens if more than one analyte in a mixed sample that we're analyzing has the ability to absorb the same wavelength that we call lambda max of incident light. In the case where we have competing analytes all absorbing the same wavelength of light, we can calculate a total absorbance as the sum of all of the contributions from all of our analytes of interest. Analyte X, analyte Y, analyte Z, and so on. it is possible to carry out a series of experiments that will independently be capable of analyzing for the concentrations of different analytes in a mixture, X, Y, Z, and so forth, by careful manipulation of our experimental technique. Here's an example. This technique requires that we know the molar absorptivities, epsilon X and epsilon Y, for our substances of interest, either having looked them up or analyzed them independently ourselves. These data in this table are collected for analytes X and Y in a UV-vis absorption experiment. Our goal here is to calculate the concentration of X and the concentration of Y in a sample that contains X and Y, where a path length of 1 is used in all experiments. Data associated with trial 1 at a particular wavelength are shown in this first row. Data for experiment 2 are shown in the second row. So, what do we know? We know that at one set of conditions, our first trial, we have a total absorbance, a molar absorptivity corresponding to analyte X, and a molar absorptivity corresponding to analyte Y. Thus, the total absorbance for trial 1 must be equal to the molar absorptivity of X times the path length for X times the concentration of X plus the molar absorptivity of Y times the path length of Y times the concentration of Y. And from the data shown in the table, our total absorbance is 1.05 in trial 1. Our molar absorptivity for X is 14,130. Our path length is 1, so I'll omit B, and we don't know our concentration of X. Our molar absorptivity of Y is 3335. Again, our path length B is 1, and our concentration of Y remains unknown. Similarly, we can develop something for trial 2 that looks like this. We take advantage of this same equation, just apply it to a different wavelength used in trial 2. Because this is a non-destructive technique, our concentrations should be the same in both trials for X and Y, respectively. Therefore, we have a system of equations, 2 equations with 2 unknowns. We can rearrange one equation, plug into the other, to solve for one of the unknowns. Suppose we wanted to rearrange trial 2's equation. We would have to solve for Y in terms of X. To do so, we would subtract 3,438 CX from both sides and divide both sides by 5532. Now, wherever we see CY up in trial 1, we can plug this whole mess of stuff in. So let's do that. We'll take this equation from trial 1, move it down here, and plug in our new expression for CY, where we saw it in the equation down below. Now, we have just one equation with one unknown. It simplifies to something that looks like this. From here, we can solve directly for CX just by combining like terms on opposite sides of our equal sign. Eventually, we come up with the concentration of X being equal to 4.20 times 10 to the minus 5 molar. If we plug this quantity back into our rearranged expression from up in trial 2, we should be able to solve for the concentration of Y. And when we do that, we end up with a concentration of Y equal to 1.37 times 10 to the minus 4 molar. Thus, it's possible to analyze for 2 or more different analytes, all absorbing at the same wavelengths, on the basis of our being able to make a system of equations that match in total the unknown analyte concentrations we've got. Here, because we had 2 unknown analytes, we had to carry out, at minimum, 2 experiments in order to deal with them. The more analytes, the more trials we have to conduct, and the more complicated our system of equations become.